Hey everyone, welcome. If you had to build a globally available, resilient, and scalable platform in an automated and repeatable manner, would that add value to your business? If so, you're in the right room. Welcome to FSI315, how JPMorganChase Payments solves for real-time fraud screening at a massive scale. My name is Bernie Hurden, and I'm a Principal Solutions Architect with AWS Web Services. I'm joined by Karthik and Jimit to talk about I'm joined by Karthik and Jimit to talk about the journey of building a cloud-native fraud screening engine capable of handling over thousands of transactions per second while protecting over $10 trillion in daily payments volume. Over the next hour, you'll learn about what it takes to build a fraud engine on top of AWS managed services, the implications of going global, and some of the lessons learned along the way. I'll pass it on to Karthik to walk us through the agenda and kick us on this journey.
To the real-time fraud payment screening by JPMorganChase. So today we'll be sharing our insights into how we leverage AWS to combat fraud. So here is our agenda of the session today. We'll be looking at payment threat landscape and then latest fraud statistics, what we notice in the industry, and then how JPMorganChase addresses the problem. Then we'll be looking at how we build the fraud detection platform on AWS. Then we'll look at what we can deliver today, some of the cost optimizations that we have gone through in the process of modernizing the applications using AWS, and finally the key takeaways. So the payment threat landscape, it's constantly evolving as technology advances and the cyber criminals become more sophisticated in engineering more fraud trends or patterns. So some of the key aspects or the fraud trends that we usually notice are phishing and social engineering. So the cyber criminals can use phishing emails, fake websites, or social engineering tactics to trick an individual or a business to reveal sensitive information like credit card details or some login information. And they can also trick an individual or a business to make a payment that is to be credited into a bad actor's account. So that's one of it. And then the other one is a card not present fraud. So as e-commerce grows, so does the card not present fraud. Now, in this specific scenario, a bad actor or a cyber criminal can use stolen information to make online purchases. And they can also use a portion of your credit card details to engineer a card testing fraud attack on any e-commerce site with the intention of making these purchases. Now, this type of a fraud is difficult to detect. Is because there is no physical card involved in this transaction. And the other one is malware. If a cyber criminal or anyone is able to install malware on anyone's computer, then the malware can gain access to the sensitive information on the device, and also the malware can act as a man in the middle where it can intercept the traffic that's going out of the computer to store the payment informations, or even can change the payload or the request payloads that are originating from the computer. And few of the other trends what we notice are account takeover, exploiting the vulnerabilities in the point of sale devices or on the mobiles to make unauthorized payments. Now with that, let's look at some of the recent fraud statistics. So 80% of the organizations experienced payment fraud in 2023. So that's a significant uptick from 2022. 10% increase in commercial card fraud year over year. 6% increase in both ACH credit fraud and virtual card fraud year over year. And 71% of the companies reported being a victim of a fraud by email. Now, if you really look at it, the year over year, the fraud instances are increasing. So the organizations or the firms should really put in the security measures to combat this fraud. And probably this is one of those metrics where the company would like to report a year over year decline. Now with that, let's look at how JPMorganChase approaches the problem. So JPMorganChase Trust and Safety Solutions protects the clients at every life cycle of in the commerce life cycle or in the payment life cycle. So we have a suite of solutions that have been provided to the client to prevent fraud. So we have validation services, which provides validating the accounts, the businesses, documents, and much more. account confidence score. This is another service that can be integrated into the payment lifecycle of clients or merchants to get a risk score of an account so that it gives more intelligence to the clients before they can make a payment. So this avoids making a transaction to a bad actor account or even preventing delayed payments. Payment Control Center is a user interface based application that's available to our clients where they can actually write rules or change the rule thresholds based on their business payments behavior or patterns. Now today in our today's session we'll be looking at Fraud Intelligence Platform. And Fraud Intelligence Platform is our real-time fraud monitoring platform. So it's based on in-house rules, which also utilizes machine learning model scores, some of the anomaly detections, and also using some of the exception list to prevent or detect fraud. So let's look at some of the high-level requirements that we pulled in when we wanted to build this fraud detection platform. So we need a real-time ingestion of these payments into the platform. So the payments, there are different types of payments, and the payments are being processed across the globe. So there are multiple applications all over. So we need a mechanism to have a common pattern or a connectivity where we are able to ingest the payments so that the payments can be validated for fraud. Analyzing the payment data to detect potential fraud. So we need a suite of services that can analyze the payment data to detect fraud. And this is where we could be using machine learning scores, checks or anomaly detections, and also the exception list checks. The system should be auto-scalable to process high volumes, especially during the holiday seasons or long weekends or month ends. You'll see high payment activity. So the system should be auto-scalable for that. And the payment activity is round the clock across the globe. So the application has to be a low latency application, but highly available and resilient. And one of the important things in the space of fraud detection is you should always have data to do an offline analysis, because that's how you proactively find out what are the new fraud trends, or even based on the known fraud, you can investigate and identify how that can be mitigated. And finally, delivering features in no time. So to mitigate or to remediate or contain any active fraud, we need to act very fast. So the system should be capable of having interfaces where you are able to tackle the fraud by introducing new rules or updating something within the system. Now, based on these requirements, where the business requirements of fraud detection and some of our technical requirements, so this is the component diagram of our fraud decisioning platform. Now, what we did here is we identified the different requirements, and then we have written out, or we have drawn out some of the components, like what would each component be responsible for. So we have request ingestion and request prioritization components, which will take in the request and do the request data validations or cleanup and then take it forward. And we have embedding signals and vendor enrichment components. So along with the payment data, you also need richer data sets to have an effective fraud solution. So we do utilize some of our vendors' data, and along with some of our banks' reference data to enrich our payments for fraud detection. So these services would be that. Feature store, we'll look in the following slides, we will be having a more detailed conversation, but feature store is used for our data transformations and also calculating some of our data aggregations. And one of the critical one is the detection service. So the detection service is the one where you would use a rule authoring application for writing rules, and also a rule engine which could detect fraud based on the payment data. And finally, one of the important one is the inference service. So the inference service is the one where the machine learning, the data scientist would develop a model, train it, test it, validate it, and deploy it. And finally, the model scores should be available through an inference. So the inference layer covers that API that's required for the model scores. And finally, the action handler, which is once you have a rule execution, what actions would you take based on the payment rule heads. So this is our component diagram. So what I want you to take out from this is we separated out our tasks with multiple components. making sure that we are able to scale the applications accordingly, because one of the important thing is handling high throughput and also processing them in low latency within few milliseconds. So having them separate out would really help us have its own deployments without impacting the whole system, at the same time scaling accordingly. So with that, let's look at the architecture. So when a payment processing system makes a request to the fraud detection platform to analyze or evaluate a payment for fraud, now that's a step one that would show up here. So the request is sent out by our payment systems. Now the detection engine within AWS is receiving the request. Now the detection engine has a suite of microservices which cohesively work to provide this full fraud detection capabilities. Now within that, we have this gateway microservice which accepts the request, validates it, cleans up the data if it needs to, and then directs or forwards the request to a decision service. Now the decision service is the critical component in the platform, because that's the place where we would be running the rules on a payment data. But before we run the rules, the decision service retrieves other data sets like enriched data or features, aggregated features, or any vendor data, and also the rules that are required to be executed for the on the payment. Like based on the payment type, the rules that you run could differ. So identification of those rules and all of these payment data sets are one of the prerequisites before running the or executing the rules. So that's the fourth step, where the detection service will be making those calls to retrieve this data. Now once we have these other data sets plus the payment data, the fifth step is all the way towards the end, is we make an API call to the ML scoring API, which would provide us with the model scores based on the payment data. So once we make a call, the model scoring API would have all of the payment information plus all of the feature data and other richer data sets based on which the scores are provided back. So after the step 5, we have all of what is needed now to execute the rules. So the detection service then runs the rules that have been identified with all these data sets. And once the rules are executed, as part of a post-processing steps, we route the request to our action handler to take the appropriate action based on what rules have been hit. So with that, the fraud detection flow usually ends for any of the transaction. And so I just want to touch base on the different components within it. So the microservices within the detection engine, it uses different data stores that you can see here. So we use Amazon Aurora for storing the rule metadata, or any of our registry, like a feature or a variable registry, and also application configurations. We use DynamoDB for looking up any of our enrichment data, the feature data, or any exception list that we need to refer to. And S3 is used as an audit log. So all the transactions that have been received by the system are persisted into or stored in an S3 on an ongoing daily basis. Now the other one, like I said, is the ML scoring API that we already discussed, where it's an application that provides the scores based on the ML models that have been deployed by our data scientists. And rule authoring. So this is one of the important component within the fraud detection platform. So the rule authoring system, which is available to our external and internal customers, would help author a rule. So it provides all the information that's needed to author a rule based on the payment data sets and all the features that are available. So your user should be able to define a feature and then author a rule, or they can even reuse an existing features and author a new rule or update a rule. So having this rule authoring UI is really important, because when we want to make a change or deploy a change of adding a new role, we don't want to be stretching out like a couple of hours to deploy a role, or even going through a process of deploying a role. So the authoring of the rule UI and having an immediate impact of the rule is really critical and important. And finally, we have the data lake. So our data lake here has all of the payment data that has been received by the system, and also some of our historical data. So the interaction between our data lake and the detection engine is through our glue jobs. So in the detection engine, so we have these glue jobs. So we have glue jobs that move the data from our detection engine to the data lake. So where it is syncing the daily data to the actual store. And also the data lake in our platform has also has this batch feature aggregations. So any of the batch feature aggregations that are performed in the data lake, we copy the data or the aggregated features at the end of the day back into our DynamoDB. So we have glue jobs which copies the data back into the DynamoDBs for a faster lookup. Now, since we bring up the batch features here, so features are really important in terms of detecting fraud. So the features can be an aggregated features, or it can also be data transformation, which can be called as a feature. So let's look at how we did our feature engineering. So what is a feature? Let me take a sample or a simple rule to explain what a feature can be. So if I just say that count of transactions is from an account is greater than 1,000 over the last 1 month, maybe stop the payments or the feature payments. If that is a sample rule, then the count of transactions is a feature. That's the aggregation feature that we are referring to. So now the features can be based on historical data, as good as till the like using the historical data till end of yesterday, or it could be end of last month, or to the end of last 3 days, something like that. Those are the ones we call as offline or batch features. And we also have real-time features which are calculated up until the last minute or even to a second. So how we did the feature engineering is, the first step is that we have a feature registry. Now, anytime we want to create a feature, the feature registry is a service that's deployed on our EKS, AWS EKS. So the feature registry provides an interface to define a feature. So as an example of a count of transactions originating or that are debited from specific or not specific account or any account is a feature. Now that feature definition is something you can use the feature registry to define it. Now all of the features that are used in the rules are defined using this feature registry. And like I mentioned, we do have offline features and real-time features. So those are the 2 and 3 here. Now both of these feature engines refer or retrieve the features from the feature registry, and they do the calculation which are in scope to the respective ones, like batch ones are calculated in our data lake by glue jobs, and the real-time features are calculated by using Flink. So the next question is like, who uses the feature registry, or who is authoring it, or who are the different consumers of this feature registry or users of the feature registry? So one of the first use cases I would say is that engineers or the product operations or fraud analysts, if they want to define a rule that has to be created as used for the fraud detection, then they can define a feature that can be used in a rule. And the second use case is in the model lifecycle. The model development lifecycle. So as part of the model development lifecycle, the data scientist can also define a feature that can be used in training and testing the model and validating it and finally deploying it. So the data scientist can define these features using the registry, and also, like I said, the fraud analyst of the operations can also do that using the feature registry. Now, once all of the features are in the feature registry, the detection engine services, the feature engine services, once they calculate the features, they materialize all of it or persist all of it into the DynamoDB. So that's the step number 4 where we are doing a feature materialization. So once the features are materialized or written out into the DynamoDB, that is where the data is being looked up by our detection service. And the most important part over here is that all the features here are calculated based on a lot of historical data, and we wouldn't really want to do that calculation in line. So we want to have a low latency system which is scalable. So all of these offline calculation and materializing this data into the DynamoDB would help us scale, and also it's been a low latency lookup for us in terms of evaluating the rules. So once all of the features are materialized, so the detection service, which is the service running the rules to detect fraud, looks up all of the features that are there in the DynamoDB Again, the features that it needs to look up, it understands it based on the payment and the rules that are supposed to be executed. So once it has all of the all of the features in place, the detection service makes this ML inference call, which goes to our model serving API to retrieve the model scores. So that's the life cycle in which the feature engineering works in our system. So the MDLC is one process of defining the feature, and the other ones are what are required for the rules. And the detection services then just use the look up the data from the DynamoDB to finally use them in the rule execution. And the model serving API here, this one is the one where the as part of the MDLC, once the data scientists have the model ready, when they're ready to deploy it, they register the model with our model serving API, and whatever models that are registered here are the ones that gets executed, and the scores are being written out to the detection service for executing the rules. So with that, let me ask Jimmy to come in to share some of the AWS infrastructure setup and configuration that helped us achieve high throughput with this platform.
Thank you, Karthik. Now, hi everyone. I'm Jimit, and I'm a lead software engineer on the infrastructure side of the house at JPMorgan. Before we dive in, I would just like to call out that in the latter part of this session, we are going to frequently reference EKS and Kubernetes. That is because EKS is our platform of choice, given the very high amounts of throughput and very low latency this platform requires. So let's dive into the infrastructure. When designing a platform that is intended to process tens of millions of requests a day, 300 requests a second, 400 requests a second, it becomes very important to judiciously analyze every single infrastructure component and network layer you introduce into the platform. Every single layer you add is going to add a few milliseconds to your processing time, and it also has its failure threshold, so you'll need to start thinking about that. So let us explore how we made some improvements to reduce the number of layers and latency in the application. So the first improvement we made was at the AWS load balancer level. So in the standard EKS implementation, you have your application load balancer, you have your underlying services running in the EKS cluster, and then you have a reverse proxy layer between the two that routes traffic from the load balancer to the underlying EKS pods. We instead selected to leverage the AWS load balancer controller. So the AWS load balancer controller is an open source plugin that helps you link the EKS pods directly into the target groups of your application load balancer, thereby completely eliminating the reverse proxy layer. So you get to save a few milliseconds there. Next, we are leveraging VPC endpoints heavily across the board. So VPC endpoints give you direct links to all other AWS services into your subnets. So, and they are known to provide extreme performance benefits. In one of the cross-region scenarios during our load testing, after we installed a DynamoDB VPC endpoint, we observed 86% performance improvement in DynamoDB cross-region queries. Next design decision we made was to choose DynamoDB tables for operations that require large data lookups. So as you know, DynamoDB tables are all standalone tables. You can configure scaling parameter for each of the tables individually. So we added more read and write capacity units to the tables that are part of large data lookups, that are part of operations that do large data lookups. And as a result, we are able to look up any amounts of data from the database within a few milliseconds. Next, let us explore a tweak we made to auto-scaling to be able to achieve the massive scale we desire. So we scale up EKS pods serving synchronous traffic based on the average CPU and memory utilization across the pods. And we scale up the pods that are serving asynchronous traffic based on the number of outstanding messages arriving, outstanding messages in the SQS queue that receives the traffic. So the tweak we made was scale early. We call it act, don't react. So an EKS pod, when launched, can take anywhere from a few seconds to an entire minute to start up and actively begin taking traffic. We start scaling up pods serving synchronous traffic at 50% CPU and 50% memory. The biggest benefit we receive from this is that when there's a spike in traffic, the existing pods that are currently running are able to consistently process the incoming spike in traffic while new pods are being launched. Next, let us talk about resiliency. So the payments, as you know, the payments transaction world is 24/7. Consumers and businesses are launching payment transactions 24/7. Fraudsters and bad actors are also active 24/7 because they are distributed across the world. And as a result of this, the platform that is processing these payments and screening them for fraud also needs to be online 24/7. So how do you build a platform that is online 24/7? You add multiple layers of resiliency into the platform so it can recover from all types of failures. In the next 3 slides, we will explore three levels of resiliency we have added into this platform. So the first level is resiliency in your underlying services. The underlying services need to be able to respond 24/7 to incoming requests. So the settings, the configurations we will show you here are going to help you achieve near zero or zero downtime in your underlying services. So the first configuration is in your application load balancer. So there are two target group modes available in the application load balancer, instance and IP type. It is very important to choose the correct mode. And we'll walk through what both the target group modes do and then come to a conclusion which one is the correct mode to use. So when you create target groups in instance type mode, the AWS load balancer controller we discussed earlier is going to register your instances in the EKS cluster directly under the target group. So the load balancer sees the nodes, the target group sees the nodes, but not the pods in the underlying that are running on the nodes. There is a drawback to this approach because what Kubernetes does is when you deploy a service, it is going to deploy the pods wherever it finds available resources to deploy the pods. And what I mean by that is, say you launch a service with a minimum 6 pods. EKS finds enough resources on one node to launch 4 pods. It will put 4 pods on one node, and the remaining 2 pods go to another node. So remember that the target group only sees 2 nodes. So it is going to evenly distribute the traffic amongst the 2 nodes. This will lead to a scenario where the 2 pods that are running on one server are going to be overloaded and may crash in case there's crash in case of high volume, whereas the other 4 pods running on the other server are going to be lightly loaded. So instance type target group is not the correct target group type to use. IP type is the correct target group to use. So if you have a service with 6 pods and you create a target group of type IP, the AWS load balancer controller we discussed earlier is going to notice that and is going to directly register all 6 pods into your target group. Now the target group sees all the 6 pods and will evenly distribute traffic amongst all the 6 pods. The next configuration setting is an annotation at the namespace level, which is the pod readiness gate. Adding this annotation to your application pod namespace informs the namespace and the target group that a pod that is registered under the target group should be only marked healthy once it is actually ready to take traffic. Now, what controls whether a pod is ready to take traffic or not? So the standard implementations of containerized services have what is called a readiness endpoint, a readiness health endpoint that you can enable on your containers. And when you enable the readiness health endpoint, you can perform basically any verifications you want as part of the readiness endpoint before sending back a success response. Now, once you enable the readiness endpoint to your service and add this annotation to the namespace, these two configurations will ensure that the pod only gets marked healthy under the target group once the readiness endpoint is sending back a configurable number of success responses. And the third configuration comes into the picture when pods are terminating. So pods will terminate due to a variety of reasons. One example is there was a spike in traffic for a while. It was addressed. Now there's no more traffic. Pods will start scaling down and terminating. When a pod transitions to terminating status, it gets marked as draining in your load balancer target group. Another scenario where pods will terminate is if you deploy a new version of your existing service. Old pods will terminate and new pods will take their place. So what we observed in our load tests is that in the default Kubernetes and EKS implementation, a terminating pod gets killed at the 30-second mark. Now, in a high volume scenario, what we observed was that these 30 seconds were not actually enough for the load balancer to stop sending traffic to a draining pod. And what we realized is that after a pod transitions to terminating status and gets marked draining at the load balancer, it takes anywhere from 90 seconds to 2 minutes for the load balancer to actually stop sending traffic to that pod. So essentially, a terminating pod needs to be alive for more than 2 minutes after it transitions to terminating status. And you achieve that by adding what is called a pre-stop sleep hook into the pod's lifecycle. This goes into your EKS deployment definition. This sleep hook is essentially a sleep command that runs for a configurable number of minutes. We have it set to 5 minutes here, 300 seconds. So once a pod goes into terminating status, it runs the sleep command for 5 minutes, and then only after the 5 minutes does it actually get killed. Only after the 5 minutes does it actually get killed. Now, be aware that this is not a blocking operation. So the sleep hook is going to run in a thread different from the threads that are processing your application traffic. And as a result, the pod will be able to continue to serve traffic even while the sleep hook is running. So these settings, these configurations combined are going to make your underlying services resilient and give you near zero downtime. These configurations are all language agnostic because they are configurations at the load balancer level and in your EKS deployment definition. So you'll be able to leverage these settings no matter what the underlying code base of your containerized service is. Next, let us explore how to make an application resilient against failures in one of the AZs in which your EKS cluster is running. So say you launch an EKS cluster with 3 availability zones. What you will observe with the standard EKS implementation is that EKS algorithms have a tendency to bunch together a large number of pods into a single AZ and only leave a few pods running into the remaining AZs. So if you have 3 AZs and say 40 pods, you will observe that around 30 pods get deployed into nodes on a single AZ, and the nodes in the other 2 AZs have have a few 4 or 5 running pods. So to avoid this kind of bunching together of pods into a single AZ, you add what's called anti-affinity to your EKS deployment definition. Anti-affinity configuration essentially repels the pods away from each other. So if I'm a pod and I have this setting in place, as you can see, this is a setting at the zone AZ level. If I'm a pod and I have this setting in my deployment configuration, as soon as a new pod of the same service tries to launch in the same AZ, basically I'll be informing the pod, hey, you need to find another AZ to run because I'm already running here. And taking this configuration one level further is the topology spread constraints. Topology spread constraints essentially do the same thing as anti-affinity, but at a server level. So if I'm a pod and I'm running on a server and another pod of the same service tries to launch on the same node, basically with topology spread constraints, I'll be repelling that pod away. Hey, I'm already running on this server. You should also not run on this server, because if this host dies, both of us are dead. And there will be an outage scenario. So these two configurations combined are going to help you distribute the pods evenly across all of the available AZs in your EKS cluster. Next, let's go one level higher to identify how we made the application resilient to failure of an AWS service across an entire region. Now, an AWS service facing an outage across an entire region, all AZs, is very, very rare, but JPMorgan is a systemically important financial institution, so we have to prepare for even that scenario. So you protect against impact to AWS services in a specific region by going multi-region. We have 100% identical platforms running in 2 regions with a clean separation between them. There is no interdependency between the services running in the 2 regions. This gives us the ability to exit a region cleanly when there is impact and resume processing in the next region. We are able to resume processing in the next region because the same underlying data is actually visible to both regions. We accomplish that by implementing replication between the data. So as you can see here, S3 buckets in both regions are replicated 2-way. We are leveraging Aurora Global Database that is deployed across 2 regions. And we are also leveraging DynamoDB global tables that are replicated across 2 regions. And so the same data is essentially visible in both regions, allowing us to resume processing from a different region if we so desire. Another design decision that is actually tied to resiliency again is isolation. Physical and logical isolation of different payment patterns. So we separate different payment patterns into their own AWS accounts. For example, credit card payments and real-time payments need faster scaling. They are synchronous payments. The volume of those payments is higher during certain seasons. So we separate these payments into their own AWS account, as opposed to, say, ACH payments or other batch type payments, which are again deployed into another AWS account. So the biggest benefit this gives us is when the transaction patterns are different, we need to scale them differently. Having completely separate accounts between different traffic patterns helps us scale them differently, helps us deploy them independently of each other, and it also helps to reduce the impact of problems in case problems arise. We also take it one step further by adding logical separation of services into their own namespaces and node groups. So services that need to work with each other are co-located in the same namespace. Yet another sets of services that need to again work with each other are separated into a second namespace. So the same principles apply to logical separation as well. We are able to scale these sets of services differently. We are able to deploy them separately and reduce the blast radius of problems in case problems arise in the future. And lastly, I would like to cover cost optimization. Now, cost optimization has to be what we always knew was cost optimization has to be a day one activity. You cannot build a platform and then go back and try to reduce the costs on your platform. It is a very difficult process once you have very high volumes of traffic. So we reserved bandwidth for cost analysis in every design decision we made. So there are 4 main pillars we follow. The first one is on-demand usage. Developers should be able to start up environments when they want to use them, but the environment should not always be running 24/7. So we have Lambda functions and workflows that go into the AWS accounts every evening at a certain time and shut down all of the EKS environments. Basically, anything that is using an EC2 instance will be shut down. The next day, these environments are not started up automatically. And developers, when they want to use them, they are free to start them up. So this gives us great benefit because we don't use all the environments all the time. Take, for example, a performance environment where you need to execute load testing. So you might do load testing for a couple of days, and then that environment might sit unused for weeks at a time. So this is the reason we shut down environments every day in case somebody started them, but we don't bring them back up the next day. Then next is the second pillar is we treat cost as a non-functional requirement. Like I said, basically every design discussion involves a discussion on costs as well. The third pillar is we have observability metrics to reduce underutilization within the environments. So we have alerting set up, that shows us the trends of CPU and memory utilization on servers and databases. We identify if there are any instances that are underutilized. We go back in and scale them down, reduce the size of the instances, reduce the size of the databases if we are not utilizing them. And fourth, we have instituted a cost champion. A cost champion is essentially a person or a team who is constantly improving the observability on underutilization and coming up with new ideas and approaches to bring costs down at all times. We imbibed the idea of a cost champion from one of the previous AWS reInvent sessions that Karthik attended. So with that, I'll hand it back to Karthik to give us a recap on what we discussed today.
Yeah, so we look at what we can deliver today. So we designed a system that can support tens of millions of transactions per day. We're able to deploy 24/7, especially with payments activity being around the clock. We need to have a system where we can mitigate fraud at any point of time. So deployment 24/7 is an important thing that we're able to deliver. And faster time to market. One of the use cases that I can discuss something like, if you need to, based on a regulatory requirement or a data sovereignty requirement, if we need to have application running in a specific region. So adding AWS region into the global instance or a global store is easier. Like we've been running our application in US East or US West, and then we want to enable a region in, let's say, APAC region. We're easily able to do it and have our blueprint, our application running there. And similarly, the provisioning. So the provisioning is really the important thing because it can also help us with provisioning the services as we need and also scale down. When we want to run some POCs, which is like a fail fast, that's easier to do and then move forward. So looking at some of our key takeaways. So we're able to focus on the business versus the infrastructure stability and maintenance. So we're able to spend more time on providing the clients with a richer capabilities or data sets that could prevent fraud. We're able to roll out features like credit card fraud testing solution to our merchants, where they can utilize to take action when there is an attack or a credit card testing attack happening on their e-commerce website. We also have commercial cash fraud detection capability started off in our AWS. So yeah, leveraging the readily available AWS services. Again, this helps us with our increased productivity in terms of really providing the actual business functionality or business capabilities here. So strong foundation is extreme scale. Now this is really important because now in AWS, one thing we were able to learn is that when we try out with a specific design, you're able to do a POC, and then if not, we're able to fail fast. So we're able to do that and establish a strong foundation for a system, and the strong foundation is really needed for the extreme scale. Because as payments activity is growing around the clock, we always need to have a system, not for today, but for the future as well, where we are able to take in higher volumes or unexpected volumes that we don't anticipate. Cost optimization and security is a day one activity. So, and all of it, while we support the clients with all of these fraud detection capabilities, the cost is really an important factor. So having a cost optimization throughout the process of AWS journey or the modernization journey is really important, and obviously the security. So these two are something that we have embedded into our life cycle or into a day one activity, right, starting from the design onwards. Yeah. So thanks everyone for attending this session, and we'll be taking in the questions. Yeah.